I want to give you a quick preview of the video you're about to see. It's a part of our Data Science Summit series. And in this session, we brought together leaders in the area of data science to help both C-suite executives, operational leaders, and technical leaders understand how to leverage data science to make better business decisions and have more predictive outcomes. It was a powerful session, and I hope you enjoy the video. I also want to thank Wilson Sonsini for allowing us to have the event at their location.
Yeah, thanks. So I'm a stereotypical Silicon Valley guy. I've done 5 startups, now 6 startups. I've had a good run, no failures. 1 IPO, 4 acquisitions, 2 still in play. 2predict is my latest gig. I'm one of the 2 founders of ChargePoint, the electric vehicle charging station company. I sit on the advisory board of MIT's Media Lab's Connection Science Group. So I get to see a lot of very interesting AI and blockchain stuff out of the Media Lab, which is really exciting. I've met some of you because we've had journey together where I've been a VP and SVP of R&D at companies like Lucent, SGI, and Riverstone, right? So that's me, I guess, right? So cool. So this morning I saw a really interesting news headline that I want to share with you, and of course it's from one of the more innovative large companies, Amazon, right, that we have. What it says is that Amazon is looking for a data scientist to study why costs keep rising, but people aren't healthier, right? And this is effectively in their first ever data scientist to join the Amazon benefits department, right? Their benefits department is hiring data scientists, right? So yeah, so that's what this is about is how do we up our analytics game? And I do believe, and I sincerely believe that data science is one way of upping our analytics game from a business perspective, as you can attest to. So there's a well-known face of AI research community, and his name is Andrew Ng. He's a Stanford guy. Cedric has taken courses from him, and he says AI is the new electricity. What he means by that is really from an impact perspective, right? Just like electricity has impacted all of us in many, it's ubiquitous. He feels AI is going to have the same amount of impact at some point in time, right? So let's go over quickly some of the key concepts that you guys have been hearing over the last few years. I'll go through this quickly because I think most of you guys are aware of this pretty well. So the first question I have, though, is how many of you think the data you're collecting is valuable? Well, you already have a cheat sheet there, but the question I ask is how do you know, right? And what we always say is that you don't know until you actually try and use the data to solve some problems and see how effective it is for solving those problems or answering those questions, right? So otherwise, it's, yeah. So let's recap what the big data definition is, right? So I'm going to scroll through this. So we've all heard of volume, velocity, and variety in terms of data. We all know the data generators, right? The data generators being user-generated content, IoT and sensors, as well as algorithmic outputs, right? Those are your key data generators today. And there was this new definition of big data called volume, velocity, and variety. IBM guys put on veracity at the end as well, right? So the problem here is volume, as we know, so there's large amounts of data. Velocity is near real-time processing versus batch processing. So near real-time processing could be autonomous vehicles, right? Where you have to make real-time decisions, right? So, and then variety is modalities like video, text, whatever, right? So data, as well as number of dimensions. So Excel speak in terms of dimensions is number of columns, right? So what I ask you is, when you're dealing with data sets with hundreds and thousands and 10,000s of columns, how the hell can you hypothesize, right? And this is where a lot of the AI techniques are very, very helpful, right? Is in helping you distill that to something that's more manageable. Okay, so what is data's role? So, we've been doing insights for a long time, right? Insights and reports for a very, very long time. So what's exciting about all this and using these AI techniques is that you can start creating models, right? And models can help you not only figure out what's going on in a more thorough way, but it can also help you predict things, right? As I like to say, I'm going to get nixed for this, but you can play God because you can predict things, right? So it doesn't work for fantasy football, though, by the way. So we'll get into that later. So in the model-based world, right, the key role for data is to train your models. Okay, that's really what it is. How many of you have heard of the racist algorithm problem? Okay, yeah. Yeah, so this is really interesting, right? So there's all kinds of examples like this, but I'll give you one that I saw a TED Talk on, right? This is where an MIT researcher was, it was a classification problem. So there's a face. Okay, is that face male or female, right? So she was training the model to decide whether it's male or female, and she was picking up work that others have done. So what happened is, when it started getting to face of color, it was predicting, well, it was inferring whether it was male or female with a lot less accuracy. And she's going, why is this happening, right? What's the difference between color and non-color here, right? And what happened is the data that they trained the models with had very little colored people in the data set, right? And that's why the model is having problems with colored people, right? So that's what I'm saying is that the data set that you train with is very, very important for your models, right? And you know, we've all heard that preparing your data is a lot of work, right? But training your model is also a lot of work, and you'll see that when Cedric goes talking about he's going to talk about in the data engineering pieces, how do you train when you have 1 terabyte worth of data, but you don't have 1 terabyte worth of memory, right? So, and he'll go through techniques on that. Okay, so learning, the new compute paradigm. So this is a very simplistic view. So in traditional programming, what you have is you have data, you call a function, right, or model, whatever you want to call it, right, and you get some sort of output, right? Y equals mx plus b, and when you pass in mx and b, and it'll give me y, right? Whatever, right? That's the traditional way, right? In the supervised machine learning case, what you have is you have data, right, and you have outputs you want, right, or they're called labels, right? And what you want to do is you want to create a model such that when you have data that you haven't trained on, that it'll give you the proper output, or label is what it is, right? And we gave you the racist algorithm use case where it was what you were training it on is this a male or female, right? So that was the output in that case, and then you have to create a model that when a new face comes in, that would give you the proper output of male or female, okay? So that's supervised learning, okay? In unsupervised learning, I've got all this data, I don't even know what it is, right? So I can't, I don't know what it's telling me. So what you're asking the algorithms to do is, okay, you know, tell me what's happening. So this is very, very researchy, right? It's basically a lot of the algorithms used in unsupervised learning are clustering, right? So you can cluster things. You can think of cluster things, okay, you can now use that as classification later on, right? And then you get into supervised learning at that rate, right? After that, right? So that's what it is. So unsupervised is, I don't know what even the data is showing me. Let me see what kind of patterns it has, right? Very research oriented. And then once you figure out, like maybe these are clusters A, B, C, D, then I can start using classification algorithms to predict A, B, C, D for future data, right? Okay? So that's really what it is. Supervised learning and unsupervised learning, that's what we're going to talk about. I'm sure Cedric and David will talk about reinforcement learning later on as well, and with some examples. So what we say here, and again, this is a very highly simplistic view, is that in ML and AL, one of the key things is not the output, but it's really the model, right? Because the model is what you're going to use to predict your future. All right, so the data science process, okay? So why are we here, right? I mean, we talked about Amazon, and they want to start using data scientists for benefit analysis, right? And so that's what really it's about. We're all corporate guys, is we want to go from data to decisions, and I would say confident decisions, right? So we've all heard this word, right? Bob, how many times have you used this phrase? Actionable insights. Yeah, right? And so my question is, how many have actually seen this? And what I'm asking is the word on actionable, right? Less on the insights, more on the actionable part, right? And this is the challenge that I think we're all facing in the corporate world, right? And how many of you are seeing this on a regular basis? So when building out a typical model-based system, this is a little maybe complicated, but I'll try and simplify it. There's really like 3 major components here, or maybe 4, right? One is cleaning up the data, integrating the data, and even reducing the noise in the data, and that is what we call denoised data sets. I put that in quote because sometimes the noise is the better signal, right? So you got to be careful what you take out on the data set, right? It depends on the problems you're trying to solve, right? Then you go through and you try and extract insights from it, right? That's normal, right? I mean, we do that all the time. Excel does that all the time. And then you build, train, and you test your models, right? And once you get a certain comfort level and probability that my model is good enough to predict this event with 70% accuracy, and maybe that's good enough for you, then okay, fine. I'll take that, okay? And what I'll do is I will run an A/B testing on my production system, right? So A/B testing meaning where A is your current workflow, work process, your current models, and let's say B is this new model, and you see how it's performing with new incoming data, right? And once you feel comfortable that the new models are outperforming your old way of doing things, the old workflow, the old process, the old models, then you switch over to the new models to help make your decisions, right? Okay? So this is kind of like the model-based systems process, right? So, yeah. If it's complicated, don't worry, we got a slide on how to reduce the complexity. Yeah.
This is a really good slide. Can you talk more about denoised data versus training data, how we delineate that? How do we think about those two?
Yeah, okay. So denoised data is, and Cedric will get into this actually, but denoised data, so you take your whole data set, right, and you reduce the noise, whatever noise is. And like I said, you got to be careful how you define noise, because sometimes what we view as noise could actually be the better signals, right? So view it as cleaning up the data, okay? Training data, so what you want to do is that's the data that you, well, like for example, let's go back to not to keep harping on the racist algorithm problem here, right? But it is catchy. So in that case, right, that was the training data set that was done to create the initial models. It obviously didn't have enough people of color in there, right? So you got to make sure that there's enough thoroughness in your training data set, right? It doesn't have to be the entire data, but but there has to be enough samples and thoroughness to it. Test data. What you want to do with test data is select data that you haven't used to train yet, okay? Right, so because that gives you your initial probability scores.
One question for me.
Yeah.
The algorithms, would you propose some algorithms for selecting or something? Or what does the box that says algorithms mean? Wouldn't this be all?
Oh, it means select your algorithms. Yeah, so whatever, so you have your models, right? And so you can see, you have to decide to create your models, which algorithms you want to use, or how many different kinds of algorithms you want to use to get whatever output you're trying to, work with, right? So it could be an ensemble of algorithms as well, right? So it's not just restricted to one algorithm.
Praveen, I got a quick thing.
Yeah.
So when you guys have a question, what I want to do is make sure it gets to the film so people that are reading and watching it afterwards. So if you have a question, raise your hand. I'll hand you this microphone. It's not an amplifying microphone, so you won't hear yourself amplified like I'm talking now, but it's actually catching it on the film. So just raise your hand if you got a question, and I'll zip it over to you.
Yeah. This is funny because I thought this was going to be the slide with the least amount of interest, but yeah, cool, all right. All right, so let's see. Okay, turnkey versus bespoke. Bespoke meaning customized models, right? So I have a thesis, and this is why we did this company called 2predict. The thesis is that it is very hard to do turnkey-based ML solutions, and the reason being is because everyone's data is different. Okay, that's the thesis. And so we created this company to do this customized predictive modeling solutions for our customers, right? Because we felt there was a gap in there, right? The gorilla in this space is a company that you've all heard of called Palantir, right? Now, Palantir actually has a platform, right? And Palantir got its fame because they were credited for helping catch Osama bin Laden, right? So, but it's hush hush. It was leaked, right? But what it is so they're. What's interesting about this? There's lots of rumors around Palantir. Are they a product company or are they a services company? And the rumors and the scuttlebutt among most people in the VC is that they're a services company, even though they sell products. And we will know for sure, and that'll be verified because they're supposedly trying to go IPO. So the numbers will come out, right, on what the margin profile looks like on that side, right? So anyway, but the point being is that they have this platform, and you have your data sets. They use their platform to integrate the data sets, whatever it is, and then they use data scientists, right, to create the models and do the predictive solutions is what it is, right? And so that is, to me, still customized services, okay? Now, where, I think a lot of turnkey tools are good for like insights, and I think where they really excel is on the benchmarking side, which I think is valuable, right? Benchmarking meaning like, okay, tell me how a supply chain organization, mid-tier supply chain organization providing this kind of product in this kind of marketplace, how do we rate in terms of our inventory turn profile, right? Well, if you're a tool vendor, right, you collect, and you have customers in that segment of the market, you collect a lot of that data, and you could provide those kinds of benchmarking services to others, right, on how they rate to your peers, right? So that's where they do really, really well. But if you want something that's really optimized for your data sets, my thesis is that you got to go something customized, right? So that's what it is, right? And then the other thing I tell is that probably the biggest test on turnkey is how long, if somebody installs a product on your network system, whatever it is, how long does it take for you to bring that system up, basically train, right, that system to operate within your environment? The longer it takes, to me, the less turnkey it is, right? That's the litmus test, is what I would say. All right, so let's go into some interesting use cases. And I like to call this disrupting old methods, and you'll see why. A question for everyone is, how many of you are seeing an ROI from your current analytics strategy? CFO guys, like, when people come with you with the analytics strategy, like, you can probably answer that better than anyone else.
My clients are young.
Yeah, okay. So anyway, so like I think it's hit and miss. It depends on the organization, right? And so I would say if you're not seeing it, then why not, right? Okay, so this is I've got 4 use cases here that I think are, and these are turnkey use cases actually that I'm going to show you. Okay, old methods, new methods, and the impact. Old methods: network security, whitelist, blacklist, right? Permit list, deny list, right? That's pretty much how the old Norton virus used to work, right? Actually, I don't know how they work now. New method. So the problem with this is that you were always playing catch up, right? An intrusion happened, right? Norton's guys are gonna have to go back and then, okay, fine, we gotta put this in the permit list or deny list, right? You know, the heartbreak virus or whatever it is, right? And then they roll it out, right? So you're always playing catch up. New method. Take a product, I don't know if it's a FireEye product or whatever it is, put it on your network, right? Collect what good behavior on your network is, right? Get that baseline, okay? Once you collect what good behavior is, then anything that's outside of that good behavior, you can start flagging, right? That would be the new method of doing network security, right? So in this way, you're always ahead of the game, okay? Credit scoring. So this is interesting. So the credit scoring system is quite antiquated, right? A big portion of it, which is what that chart shows, is you have to have payment history, right? Which means in order for you to get credit, you have to have credit, right? So students typically don't have that, right? Because they're on their parents' credit cards, right? So many of you are parents. So, right, so they don't really have a real payment history, right? There's over 2 billion people in the world who don't have payment history from a traditional sense, right? They do cash transactions, right? How do those get logged, right? So, so part of the new methods, one of the things that's great about our world is this is better than a computer, right? This little thing. It has amazing amount of sensors. Your computer doesn't have these sensors, right? GPS signals is one of them, right? And so what you can do now is model people's behavior, right? Model where they go, when they go, where they go next, and you create a behavior profile. Okay, and maybe that could be a better predictor of how good of a credit risk you are. Okay? By the way, all these are real use cases. I have companies attached to all of them. So the cool thing about this is, not only do you, can you now figure out whether a student is credit worthy or not, but you can also include the 2 billion people in the world who don't have access to credit, right? So, by the way, let me digress on here. So my wife and I were fortunate enough this is a funny story on credit actually, is to be invited to dinner with Muhammad Yunus. I don't know, how many of you know Muhammad Yunus? It's just a group of 50 like this, yeah, right? So he's the father of microfinance, right, is what he's known for. And his whole thing was that the way he started was he was seeing all these villagers. They'd get up in the morning, right, and they'd need cash to go do their daily business, right, and bring in the cash and then feed their family, so to speak, right, which is great. And so he asked all the banks, why can't you do this? It doesn't cost much money, like these daily loans, right? And the bank wouldn't take the risks. And so he said, I'm going to start Grameen Bank, okay, and he's going to take these risks. Okay, great. And so what wound up eventually happening is that he felt that women were more apt to repay at the end of the day than men were. So in the end, what wound up happening is if you're a woman, chances are very high you're going to get that daily loan. If you're a man, it's a little, gender bias. So anyway, my point being is that there's different ways of credit scoring, right? So, okay. Another one is call centers, right? So I don't know about you, but I get frustrated calling call centers, right? It's like I just had an Xfinity experience I don't know, 2-3 months ago, right? As you can tell, I'm still resonating from it right here. So you know how the drill goes. They're all doing their job, right? Is what it is. They go through a static script, right? It gets very aggravating. And even the call trees are ridiculous nowadays, right? It's like, how many steps do you have to go through to get to someone, right? I want to pay 0, 0, 0, right? There's a new way of doing it, right? How about we give the call center rep a tool, and what the tool does is it tells them how effective the dialogue is. And it'll tell them things like, hey, the person on the other line sounds very tense, or hey, you guys are having overlapping conversation. So now the call center rep can actually change what they're saying and how they're saying it in real time, so you have a more effective dialogue, right? And so the way that's done is through intonation modeling, right? So it's not doing natural language processing, right? It's actually modeling your tones, right? Your intonation here, right? And what the cool thing about that is now you can take that because it doesn't do natural language processing, because words aren't honest, right? Your tone may be more honest than your words, right? It's from the honest signals, concept here, right? So now you can actually take that because it's not doing natural language processing, and you can move it from English call center to like a Korean call center, or to an Indian call center, right? Because all you have to do when you install that software is retrain the models just based on intonation, right? Pretty cool stuff. Oh, and there's a side benefit to this as well, which is really cool for this company. Is after you get done with the call center, they give you NPS survey, if you will. How many of us really take it, right? Yeah. Oh, you do? Okay. Yeah. 1 out of whatever, right? So, yeah. So, so you know, it's low participation rate on these NPS surveys. What happens here is you don't need to do these surveys anymore because you get 100% feedback on how the call went based on the intonation modeling, right? So, this one is I thought I'd put in here is it's the mental health. Okay, so it goes back to this guy again. Lots of interesting sensors here, right? Much better than computers. So what I've been told about mental health, if you want to be diagnosed with mental health, you go to see a trained clinician, right? You know, an expert, and they do a Q&A, okay? And based on the Q&A, they will determine with the state of your mental health, right? So, well, you know, my mood today is different than my mood 2 days ago, right? So, you know, like, so they're trained to work through all that stuff. Well, but it tends to be very error prone because it's a Q&A process, right? The other thing that happens is, let's say you get diagnosed with bipolar or PTSD or depression or whatever, right? Now they'll prescribe you some sort of cocktail of drugs, okay? And you go take the drug, you come back a month later, and you go through the Q&A process again, okay? Again, error prone. How well did the drug go, right? How was the efficacy of it? Again, error prone. Well, this thing over here captures all kinds of data sets again, right? So there's this one startup, what they're doing is they look at your GPS signals, they look at your call logs, your SMS logs, and a couple of other data sets. And based on that, they can tell you how effective, and they can tell you the symptoms associated with PTSD, bipolar, depression, a few other things, and as well as diagnose it for you as well, right? And based on that also, they can also tell you how well the drugs that were prescribed to you went as well, right? So it's less Q&A, it's assisted, it's assisting the physician in that sense, right? So those are cool stuff you can do with AI, right? And these are turnkey solutions. Okay. All right, now let's talk about a couple of other things. Let's talk about marketing and supply chain as use cases here, right? So marketing, you know, I mean, there's plenty of marketing folks here. Everyone struggles with this whole notion of marketing qualified leads to booking ratio. How do you increase it? How do you increase the conversion rate? How do you accelerate the velocity of conversion, right? I mean, it's a constant battle for all of us, right? So if you have the data set, right, if you have enough data log, whatever that means, right, you know, you can do things like integrate your marketing automation platforms like Marketo, right, and your Salesforce platforms, integrate the data set, and maybe you can come up with an idea of how to increase your conversion rates and your velocity rates, right? But again, the data has to be there, right? And you know, I think a lot of people have a good sense of whether their data is bad. I don't think people have a good sense of whether their data is good, right? Supply chain, right? Like I think we were talking about earlier today, right? Like how do I increase my inventory turns ratio, right? From whatever number to whatever number, 4.0 to 4.5, or how do I reduce my expedited shipments by 50%, right? So all that is a forecasting problem at the end of the day on a SKU by SKU basis. That's the bottom line. That's in a very simplistic sense, right? And again, what kind of data are you collecting, and whether your data is good enough to do the kind of modeling is TBD, right? So you don't know it until you start going through the process. Yeah.
I'll get a mic.
Yeah.
So can you please explain, for example, the first one, and you say my NQL booking ratio is 10%.
Yeah.
And you say I can make it be 20% with a model.
Yeah.
Can you explain how that happens? I mean, does the model analyze the data that
Yeah. So you could do things. Yeah, you could do things like. So one of the results might be from there. I'm just theorizing here, right? So one of the results might be is okay, like the data you might have to have is actually the campaign data as well, right? And you can also do an analysis of which campaigns are more effective at doing the conversions, right? And which campaigns are not. So you might come down to the point where, okay, as a result of that, Bob, right? He used to be CMO extraordinaire, now he's a sales guy, right? it might be like, you might say, okay, as a result of this, in order for me to go from 10% to 20% conversion rate, I'm just making up numbers right now, right? Is these campaigns are most effective, so I'm going to double down on these campaigns, right? And these campaigns are not effective, so I'm going to scale back on those campaigns because those are a waste of money, right? Those are things that, those could be the output, right? Yeah, I mean, customer service, so, you know, the renewal rate is always a big issue with customer service, right? And again, does your CRM and ticket handling systems have the data sets so that you can answer the questions of like, how do I double my renewal rates, whether it's 5% or 10% to whatever you want it to be, right? But these are models that you can try and you know, well, first of all, you're going to go through the insight process, and then you're going to have to go through the predictive model process. But the one cool thing I want to emphasize here, and I didn't mention, is when you go through the process, Bob, is that one of the cool things about the process is you will have an understanding of what gaps in your data exist, right? Because you're trying to answer this question, and that question might be answerable with like 50% accuracy or 60% accuracy, but that's not good enough for you to make a decision on, right? Or it might not be good enough for you to make a decision on. But what it is like during the process, what you'll get is, well, if I collected this kind of data set, or if I collected this other kind of data set with higher quality, then maybe I can increase my probability and confidence level from 60% to 70%. So that right there is also a very valuable process as well, right? And this goes back to the very first question, is how do you know how valuable your data is, right? But this will help, you know, the process helps. Sensors application, so this is interesting. We just did a project actually on this with a large oil and gas company out of Houston. And what they have is it's hydraulic fracking. As those of you that know me, like I said, I was founder of ChargePoint, so you're laughing at this. So what they have here is that, so hydraulic fracking, as I've learned, is you drill vertically and then drill horizontally. It can be called horizontal drilling as well. And it can be like it's 1.5 miles long, right? And during the drilling process, what happens is the top side of the drill is turning, the downhole starts turning at a slow rate for whatever reason, basin characteristics, whatever it is. Torque develops and drill bits break. Once the drill bits break, you pull it out, right? You need to replace the drill bits and whatever, and then continue down the process. So we got a data set of 5 different wells, having 31 failures, costing 45 days of downtime, right? And what they wanted to be able to do is, based on the topside sensors that's located on the drill, be able to predict when the drill bits were going to break, okay? And so we went through the process. We gave them a lot of insights, Cedric and David gave them a lot of insights. We created a predictive model. We found a correlation with lateral vibration, okay? And we were able to give them at least 2 minutes heads up that the drill bit was gonna fail. And so in that at least 2 minutes, they can stop the drill, they can pull it back a little and maybe take a slightly alternate path, right? So now the issue is that we're going through the process now. They had 31 failures. Can you reduce that 31 failures down to 15 failures? Or, you know, that's TBD right now, but we're going through that process, right? So that's a perfect example. That's a predictive failure example, right? Okay, so what is really, really difficult? So this is me slightly pontificating, and you guys can tell me that I'm full of you know what. All right. If someone tells you they can do this, run away. Predicting the stock market. Yeah, no, how many of you, I'm sure many of you have seen like Yale teams, Harvard teams, MIT teams saying that they're going after this problem, right? And they raise a hedge fund, right? They have a new method, new algorithms, whatever it is, right? It's very, very hard to predict this, right? And a lot of it is, you know, one theory is that in the short term, a lot of it is sentiment driven. The issue is what drives those sentiments, right? Geopolitical issues, and where are they captured? Where's all that data captured, right? It's never in one place, right? So anyway, that's hard. So this is another one. So I'm seeing a lot of startups that want to use social media data to do some behavior modeling, like credit modeling and everything. What my thesis here is that if it's social media is not honest signals, right? What you put on Facebook, right, is what you want to project to the world. Okay? So if you're relying on honest signals, right? If your models are relying on honest signals, you can't use social media data, right? If you can get away without having to rely on these honest signals, if you can rely on what people are projecting, like sentiment analysis might be a good way for social media, right? If you want to do sentiment analysis, that might be good. But in terms of like credit scoring, it might not be good, right? So you got to decide, right? Intuition. I don't know, like, it's like, yeah, how do you model intuition? I mean, I guess you could, right? Like, I got 5% of data, and then I'm going to guess on what was going to happen based on 5% of data. That's a hard one. And then singularity, right? Singularity, my definition, I think most people's definition is, you know, machine IQ is greater than or equal to human IQ, right? So, you know, people are working on AIG, AGI, artificial general intelligence. By the way, that's, is it Ava from Ex Machina? Is that her name? Yeah, right. So, you know, we're not even close to that right now. I would say like the next big step towards singularity is if you can pass the Turing test via chatbots, right? That'd be the next cool step, right? The Turing test is like if someone's interacting with something, right, and they can't tell with a certain degree of probability whether it's human or machine, right? So imagine that with a chatbot interface, right? It's the Turing test. Yeah. Anyway, but it's fun. I mean, you know, we'll see where it goes in 10 years. Yeah. Okay. Let's talk about the data science strategy. I think. Yeah. So anyway, how many of you are truly excited about achieving actionable analytics? Yeah. Okay. Me too. I didn't wait for a response. So Bob. I've learned a lot from Bob in my old days at SGI. So, you know, he went through SWOT analysis or drove us through SWOT analysis and Hoshin planning methods and all that stuff, right? Remember that, Bob? So, you know, I think part of the development process, if you really want to data science practice and you really want to do it internally, you have to go through this kind of a planning process. And I think it starts with the visions and goals and the metrics, and actually doing your SWOT analysis, right? SWOT being strengths, weaknesses, opportunities, and threats, right? And part of the SWOT is actually figuring out what your current data set is, right? What your culture is, because one thing about data science is it's researchy, right? And not everyone can manage researchers, right? Research is not a plan of record thing. Research is maybe a plan of intent thing, right? So, and then, you know, so even on the leadership has to be able to manage researchers, right? So it's different skill sets. And then also the risk investment tolerance. Then from there, you know, you can do your strategy development. And the key outputs of the strategy development and the operating plan would be obviously your strategy, but your organizational structure. Do you want to go horizontal or vertical, right? One of the reasons for going more of a horizontal structure, if you got many business units, is that data scientists are hard to find, right? There's a big supply-demand gap, and I'll show you why, right? So, the other thing is that you know, maybe consider doing an analytics roadmap, right? Where what the analytics roadmap is questions you want answered at what point in time, right? So, you know, which is a good way of converging the organization towards goals. And then an operating plan, you know, which is all the budgetary stuff and everything. So from a resourcing playbook, obviously the considerations are your abilities and capabilities, your risk tolerance, timelines, right? Because you're going to be spending dollars, and you know, your peers are going to wonder what's the result of those dollars. So the CFO is going to wonder what's the result of those dollars, right? Learning curve as well, right? So, you know, if you're not an organization that's used to managing researchers, right, there is a certain amount of learning curve. If you're not used to being a data-driven organization, there is a certain amount of learning curve there. And then the cost, right? And so what you get from there will be the organizational structure, horizontal or vertical. Vertical meaning it's embedded inside the business units. And you can decide, do you want to do in-source, outsource, or do you want to do an out-and-in strategy where you do outsource first and then you bring it in-house later on, right? That's a valid thing. Because what the benefit of doing outsource and then bringing it in is that you get to learn from external people, right? And you can see what's working and not working within your organization, and then you can formulate a strategy based on that. Co-creating projects as well is also another strategy where you hire a small skeleton data science team internally, and then you use the outsourced guys who are experts, and you work on projects together, right? And you can pick up best practices from there and bring it inside as well, right? That's always fun. And then onshore, offshore strategy, right? Like I said, there's a supply demand gap in the U.S. and a lot of the Western countries. So a proper offshore strategy, and as we all know, offshore is not easy to do, can drive the cost down. And I'll explain what the cost differential can be. So I'm not going to go through everything here, but I wanted to compare a little bit of senior data scientists versus software engineers and data engineers, right? The really good ones right now are going for, from here, Bob's going to want to go back to school and be a data scientist. Yeah, right? Facebook, Google, all these guys that are snapping the really good ones are $400K to $500K a year for a senior data scientist right now, right? You can get Eastern Europeans for about a third of that, right? Yeah. And what I tell people is it's actually 2 to 3x that of senior software engineers, right? Is the equivalent level. So it's very expensive. The language of choice is Python, is the language of choice for data scientists, right? Where Java, C++ is for software engineers, right? Where software engineers are also good at taking it into production code, data scientists are not production code guys, is what they are, right? So one thing you might want to do is if you need to productize something, right, what you do is you hire data scientists to create the models in Python, that's their language of choice, right? And you hire software engineers to take what they have and convert it into Java so then and embed it in the product. Okay? All right. Too daunting. Don't worry, we got a playbook for you. Okay. Maybe a walk before run strategy is here's what you do know. You do know what problems you have, right? That's the most important thing that you do know, right? What problems you want answered, what questions you want answered. What you don't know is how good your data sets are for answering those questions, right? So one solution is learn before committing to a strategy. So what you can do is, you get your data, pick a valued business problem, what we call a quick win, right, or quick look, if you will. Pick an internal project manager, work with an outsourcing outfit, and make it outcome-based. Make sure it's outcome-based, right, versus just consulting services, right? And then make it milestone-driven, and then review at the end. And if you do this, right, and you do it properly, what will happen is you should be getting some amount of analytics that you can take action on, right? And that'll make your CFO very happy, right? Because it's actually actionable analytics, right? Number 2 is you're going to get data gap analysis, which is very valuable on what your future data strategy should be, what your future data collection strategy should be, right? It'll help you define that, which needs to be part of the roadmap as well. Okay, and the third thing is you're going to get knowledge, right, on how to manage data scientists, how to manage, what your outsource and in-source strategy should be, what your offshore onshore strategy should be, all that stuff, right? So all that will feed into your strategy, and so that's one thing is rather than tackling it all at once, maybe walk a little bit and learn. A quick win strategy, so we call it actionable insights. So we said start with valued questions. So does online ad spend and CIO magnitude result in marketing qualified leads? Right, that's a question, right? That'll be a question that you'd ask, right? So, well, not actionable. Yes, it is correlated. Okay. What if I told you this? It is correlated, but it's weakly correlated with a correlation coefficient of 0.24. So probably better to reallocate those dollars to somewhere else. So 0, this correlation coefficient goes from -1 to 1, right? 0 means no correlation at all. right? And so 0.24 is weakly correlated, right? So maybe that's a better insight, right? How do we reduce our expedited freight charges, right? Well, here's a report on SQE, on expedited freight per SKUs, right? SKU, per SKU, whatever. How about if we do, it's like if we take action A, our predictive model shows that with 78% probability that we can reduce expedited freight charges by X dollars on the top 3 SKUs, right? So now the question on this is 78% good enough for you to make that decision, right? In most cases, it probably is, right? It's probably worth a try, right? So these are the kinds of results that you want to look for. So in conclusion, I think your big data potentially stores significant value. I think we all believe that. AI skills is the key to extrapolating value from your data set. Modeling allows you to predict the future and make confident decisions. Data scientists possess key skills to create these predictive models, right? And your data science strategy must be dictated by your needs, capabilities, and constraints. And one of the things that's exciting about me is that we've been hearing the word data-driven decision for the longest time, decades, right? I feel like that era is finally here. So, thanks.
Questions? Anybody have questions?
I have some comments.
Yeah, go ahead. Sure. Comments are okay too. Remember, you're not going to hear your voice amplified here.
Okay. As somebody that's been in this field for a long time, doing a lot of predictive modeling and stuff like that, I always find that we're missing the front end of this. And that is, you can't do very accurate predictive modeling if your process is not stable. If you're trying to model data that has a lot of out-of-control type data points. So one of the first things that we've got to address is the stability of the process. You do that through statistical process control. Identify assignable causes that you can eliminate and get down to the true process distributions that you're going to model. Secondly, a lot of times the data we collect is badly obtained. People don't know how to design experiments in industry. I've been in industry a lot where engineers have to learn how to use statistically designed experiments to get the kind of data that they can easily interpret and understand. So those two issues have to be put in the forefront before you start doing any of this kind of predictive modeling or data analytics.
Other questions? Comments? Questions? Yeah.
Yeah, I have a question. So, Praveen, this was really good. Some really good, real depth and insights. I like the way you, at the very end, you had those examples about correlated, not correlated, weakly correlated. And so I'm in a business which is, I don't work for Looker, but I'm in the same space as Looker. These platforms used to help non-data scientists get actionable insights and behave like data scientists. And you went a quantum leap beyond what that world is about. Right? I mean, that's the world you play in at 2predict. Help me understand, where do I think about that gray area where you need a data scientist versus using a platform that makes business people think like data scientists? At $400,000, $500,000 a head, that's a very expensive resource with great return. But how would you coach an executive to think about that? Because that's a hot topic right now among a lot of execs with this crawl, walk, run, and how they invest.
So I think what I would say is that this is my personal view, and people chime in, is that I think there's a lot of organizations that don't have good analytics in the organization as well for various reasons, including the front end of the process, if you will. So those kinds of people, I think they're happy with just insights, right? They're not even thinking about predictive models at all, right? So, and I think if we're going to go down that path, then I would take a hard look at tools, right, and platforms, if you will, right? So, and I think that would be a good walking way of doing it. And I think what I've seen is that a lot of people have invested in the last few years in the front end. There's a lot of tools to do data integration and data cleaning and all that stuff like that. Some are good, some aren't, right? All that stuff. But what I worry about is that that's all great in data lake architecture and all this stuff. That's all great, but I think I feel that they're still not driving to a value, right? They don't see the value yet, right? It's just it's a spend, right? It's not value driven yet, right? And so what I would recommend is on the walking side, I think whatever you decide to do, don't just focus on the front end of collecting, integrating all this stuff. Start working on, layering on like some valuable insights, right? Because I think your CFO is going to demand, your organization, your whole company is going to demand, like, I'm spending X amount of dollars. What results am I seeing? What's the ROI here, right? So I think you gotta play both sides a bit, right? But not forgetting that you have to architect it properly up front as well, right? I mean, the whole the data acquisition strategy actually is a big problem, right? But I ask you again, is that you have to have a data acquisition strategy no matter what you do, but you have to understand how good your data set is before you can develop that data acquisition strategy, right? And what I'm advocating for is start playing with it and start asking questions so you get a sense of how good your current data set is, right? That way you can develop the data acquisition strategy.
Other questions? Yep.
Praveen, great presentation. I love the example you gave about the drill bit fail and looking at correlations in data. I think in that situation it's kind of one-to-one, and there's probably other factors. When you get into more traditional kind of demand planning, forecasting, classic supply chain stuff, any examples of how you guys have inserted yourself, found correlations, because there's just so many different inputs of data, whether it's sales teams, you have operations teams, and it's, that's, just be interested in any insights that you found in that area.
So we haven't worked on any such use cases right now. No, Cedric, have you worked on any such use cases? No, I don't think we've worked on any of those use cases, So I can't give you a concrete example. I can only give you what McKinsey report kind of stuff is, right? But that's kind of useless, right? So, yeah. But on that drill bit failure, it was a 0.74 correlation from topside sensors, from lateral vibration to predictive failure is what we found, right? And in that example, they thought that 0.74 was probably good enough, right? And so they're actually doing A/B testing in their labs right now.
Thanks again, Praveen.
Yeah, thank you. Thanks a lot. Thank you.
So I'm a second-year PhD student at Stanford, as Praveen said. And prior to coming back to school, I spent about a decade working in the oil and gas industry. And I started my career with a hard top, going to oil fields and banging on pipes, and then kind of worked onto more office jobs and more toward the end of my career, my short career in oil and gas, I started managing a team of data analysts, and this is how I got interested in this whole topic and decided to come back to Stanford. So this career took me to various places in the world. I spent about 2 years working in China, 2 years in the Middle East between Kuwait and Iraq. I spent a year in Colombia, a year in Mexico. And if my accent doesn't give it away, I'm originally from France. So today I'm going to talk about a bit of the hidden work that goes beyond all the magic that happens when we talk about deep learning. So very often it happens that you have teams of statisticians and data scientists and engineers that crunch the numbers and really produce the insights. And as much as we want to make the story very romantic and say that, oh, you have this brain plugged into a computer and suddenly everything is going to get resolved, it's really a matter of grinding through the numbers and trying to form hypotheses. And this is where the true value gets generated, I believe. So the agenda today, I'm going to start with a problem statement and talk a bit about the different challenges, and then talk a bit about data engineering and the different techniques that are used to prepare all of those workflows. I will then go so I'll start by giving you a couple of intuitions about the problems and then go into practical examples. I consider myself a technical guy. So I'll have a tendency to jump into details, so don't hesitate to stop me whenever I get too caught up. And all the examples that I'm going to go through today are examples where I was personally involved, that I personally coded. So if you have any questions, please don't hesitate. I'll talk about traditional approach to data cleaning, and I think there were some questions on Praveen's presentation. And then I'll go into maybe a bit less conventional approach and things that we are happy to experiment, where we leverage AI to prepare data for AI models. So the problem statements start with this cartoon. I don't know if you see it from there, but I found it very relevant to the problem that we're going to talk about today. And you have this guy who is asking, oh, this is your machine learning system, and the other guy who's sitting on a pile of data just says, you just ram all that data through this linear algebra, and then voila, everything is magically appears, and what if the results are wrong? You just steer it again and try to until it starts looking right. And I guess this is going to resonate with some of you, but the whole idea of having black box solutions, and when I went to school, my professor were always talking about garbage in, garbage out kind of approach, gets amplified when you talk about machine learning and data science, because you rely so much more on the data and a little less on the heuristics and the physics. So if your data is not right, your model is essentially garbage. So there is a whole contentious idea that, let's say, early 2000, we started having statistical models, statistical learning, shallow learning, which still relied heavily on feature engineering, and that with the rise of deep learning, all of these things magically disappeared, and now deep learning is taking care of everything. You just ram in the data and the system figures it out. I think the reality of the field when you start solving real-life problems is very different, and data cleansing and preparation is, if not the most important one, of the very important steps in the data science workflow. So the data must be transformed, it must be standardized and put through a given format. Different companies have different processes, and very often when we approach a client, they will tell you, oh, my data is clean. Everybody thinks that they have like the perfect data. I think there's no such a thing. It's clean until you ask the question that makes it break. And this is why we have certain workflows to that we go through to guarantee that our data is right. So very quickly, I'll go through this. The first step is data formatting. All of you have data in different formats. It could be CSV files, it could be export from database, it could be a bunch of PDFs. So you need to format it in according to certain standards. Then you need to, an important step is the matching. So you constantly need to question your data. Everybody again believes that they have clean data until you question it and cross-reference it with something else. And the last project that we've worked on was a perfect illustration of that. I'll go into it a little more. Then the data loading is really something that relates to what Praveen was talking about, the difference between bespoke versus turnkey kind of model. We tend to see that smaller customers and smaller teams prefer to have a database logic, and larger teams and larger institutions work with database structure, framework, and infrastructure. And you need to be able to essentially work with both. They both present advantages and drawbacks, but it's an important step of the workflow. And I put data visualization at the end, but it's really something that you do all over the workflow. There's nothing like looking at the data to try to understand it. I put it at the end because typically data scientists' end product is a nice dashboard that they would create in Jumper or Spotfire or Tableau, all these business analytics tools, so that executives like you can essentially query their data and start making decisions. But really something that a data scientist needs to be able to do very, like all along the workflow. So let me, again, I'm going to introduce a couple of concepts over this and the next slides, because I think they're important to understand why we do or what we do. The first paradigm that I want to talk about is the modeling, inference, and learning, which is a well-known paradigm in artificial intelligence. And essentially, each machine learning workflow will have to go through these different steps. The modeling, we understand, is the world is a messy place. You are trying to essentially translate all that mess into a mathematical abstraction that is amenable to a computer system. So you're trying to make the problem solvable by a computer. And this is the part I'm going to spend the most time on. Then inference is essentially inventing a set of rules or algorithms or methods that are going to be allow you to make predictions based on the model that you have created. And the whole learning part is the part that David is probably going to dive a bit more into, is how do you confront all of these inference to the real world and essentially adjust your vision of the world and your inference system to have something that makes sense. Or like the cartoons say, you just steer until it starts making sense. But ideally, you would have a first guess that is not too far from the reality. The second concept that I want to introduce here is various level of insight. And in that chart, I use insight not to say intelligence. In that chart, what you're going to see is on the left, low level of intelligence, and on the right, high levels of intelligence. And Praveen was talking about the various hard problems until the singularity. I'm not going to go as far as that. I'm just going to introduce things that are existing right now, and toward the end, probably state of the art or things that are probably going to arise in the next few years. And the first type of models are reflex models, and the perfect illustration of that is computer vision. And they are typically a feed-forward kind of model that can feature networks that are very deep. And this is the first distinction that I want to make between intelligence and deep. We tend to believe that if a network becomes deeper, it's going to magically become more intelligent. It is not true. Those networks can have like hundreds of layers that are stacked, but the task that they solve by nature is extremely simple for what we describe as intelligent or insightful as a human. The second type of models are states model, and the perfect illustration of that is the chess game or the game of Go. So Praveen was talking about the different type of model, supervised and supervised. Reinforcement learning is a rising type of model that help and that have performed extremely well in those rule-based games. Where there is a sequential set of steps that the agent needs to take. So they represent an advance compared to the reflex model. The third type of model are variable model, variable constraint model, and those are the center of the technology that makes self-driving cars, for example. And the idea here is that the problem is entirely defined by its constraints, and it's just the way you navigate or connect these different constraints in a deterministic or probabilistic way that allows you to have a running agent. And those work very well in a system where the rules are not as well defined as in the game of chess, but are more applicable to real life kind of situation. And then the holy grail would be logic. Logic was at the center of artificial intelligence for about 2 decades in the 60s, 70s, and was almost the reason why artificial intelligence almost died, because we were not able to crack that tough nut. And recently it's coming back. But the way I perceive logic is, as Praveen said, the Turing test, or more having like the personal agent that is able to essentially follow you everywhere. And we have like a kind of a pale attempt at doing that with Siri or Alexa or Google, Hey Google. But the way I see it is like Jarvis in the Iron Man movie. I don't know if you've seen that. That's kind of the goal to reach there. So the important thing here to keep in mind, again, is depth doesn't mean intelligence. And there are a whole set of different paradigms that are useful for us, especially in industrial application, to generate insight and actionable insight especially. And the last piece on like conceptual stuff that I'm going to talk about is so the learning framework. So learning is essentially feeding data into a system and forming a predictor that when faced with new data is going to give an output that makes sense. So can we just feed raw data to a predictor? For simple tasks we can, but in any case you always perform more poorly when you feed raw data than when you feed feature data to a system. So this whole debate around deep learning being able to kind of get rid of feature engineering is kind of moo, because it only depends on how far you want to take your algorithm. So you will note here, I won't use too much mathematical notation, but the raw data is typically referred to as x. And the input to the model is f of x. So you extract features from that raw data typically to kind of help your model. And this is all what we are doing here. So domain expertise, logic, and our own intuition help us design features that are going to be very useful for a model to solve a task that can be more or less hard. And the example that I have, sorry Praveen, I think that's the only picture of you I have. Is the face detection, right? You could feed a simple image, but there's always a layer of processing that you do on the image, whether it's the transformation from pixels into some form of digital format, some kind of filtering that you do on the data, the cropping, etc., to the different points of a face that essentially give you a lower dimension representation of what a face is. And I'll go through another simple example to kind of nail this issue. Is like, what if we were trying to predict whether a string is an email address or not? So you could simply feed that string to a system and expect, if you had like millions of those and just classify them as email versus non-email, you could expect it to find a solution. But you could solve this problem very quickly if you were to decompose that original string in a set of features, whether it has a certain length, a fraction of alphanumeric characters, contains certain symbols, ands with this and that. And one of the problems with feature design is that you very quickly run into what we call the trade-off of sparsity versus general representation. If I wanted to engineer a feature that would tell me with what character the email address finish, I could start by having 26 features for each of the letters. And then if I went into the combination, so the combination of 2 letters, 3 letters, and 4 letters that finish an address, you can see how the number of features could explode. And most of those features would be 0. This is what we call sparsity. And if we want to be general, we would have to have a very large, very sparse representation. On the other end, and we will see that later, you have ways now with encoding to come up with denser representation that are both usable and don't need, and also very general, that can be trained on the spot. So I hope with these I have motivated the necessary use of feature engineering to solve some problems. And so just a quick example is like, is feature extraction obsolete? So if you wanted to show a picture of a car and decide whether it's a car or not, probably. But if you want a car to drive itself, I think you still need to do quite a bit of grinding and feature work and feature engineering. Okay, so now we're going to go through a couple of examples of data engineering that we have applied at 2predict and on the various projects that we've worked on. So the first one is we have to realized that when we start talking about big data, it's very common now for companies to have data set that goes beyond a terabyte of data. It's something that we face every day, and we need to find a good structure to store that data and at the same time be able to efficiently query it. So what we have kind of converged upon over the past few months is, I think, what is the state of the art for a lot of people, which is the Apache Parquet format, which is extremely efficient in terms of space storage and also into query speed. So on this chart, I show a comparison of HDF5, which was, I say, the previous state of the art, and Parquet, and what you have in the y-axis is the time to read a typical set of data, and then how much space it occupies. And what we see is that the Parquet, and you have different type of format, whether you use parallel computing as well, tend to outperform HDF5 on like a very large benchmark set. So we have used those quite extensively in our most recent projects. The second set of tools that or we use are visual. So as I told you, there is no better way to query the data than just snap it in front of an expert and let them essentially question it. So we use Jumper, we use Spotfire, we use all of these business tools, business analytics tools to create all of these dashboards. So those are coming out of the drilling example that we're talking about. So what you see here are a set of wells that are drilled in the Permian Basin in Texas, mostly on shale. And what has happened over the past few years is that the shale revolution was the result of an extreme improvement in efficiency from the drilling companies that were able to drill wells in probably a third of the time that they were in the past. So you went down from a well taking a month to drill to about 10 days. And that is the big difference between shale being profitable and unprofitable in any kind of price environment. And it started with things like that. So I talked a lot to some colleagues, and it was a game of minutes, of hours, and how do you essentially become more efficient by having a very unbiased assessment of what we call the non-productive time. And what you see on the top chart here is non-productive time. And then once you have nailed that down, how do you define the different phases that were non-productive and the things on which you could have an impact. And it all started with that kind of dashboard. And yeah, I could go through a lot of those, but that's not the purpose here. What is important is that not only visualizing is important, it's also important to be able to interact with the data. And this is where we talk about human-machine interface. And the tool that we had created here is a tool for data labeling. So typically, if I snap a dashboard like this on Jumper or Spotfire in front of an expert, they can very quickly spot whether some data doesn't look very right, or they can even start to manually interact with the database and try to correct that. But typically, you lose all of that experience as soon as the expert is done with its work. So what we have created here is a tool that would essentially be part of a whole workflow that an expert goes through when they do data labeling or classification. And what it does is this similar type of chart as before, where you have like the time versus depth of well, and you would be able to select a certain section of the well and have data pop up. And what you would see here would be whether your client has classified a certain point as or a certain time as non-productive versus productive. This is obviously something very subjective. So if you ask a service company their non-productive time, they will tell you it's down to 1% because they're getting paid for it. The person who pays for it will tell you it's 40%. And as a data scientist, you kind of have to strike the right middle and be as unbiased as possible. So the way the tool would work is take an original assessment of this non-productive time, then an expert would go through each of the lines and start classifying by hand and say, well, I believe that this was non-productive, this was productive, non-productive. And then you would run that through a machine learning algorithm based on natural language processing that would link a bit like the spam versus non-spam or the whole sentiment analysis, whether a certain time was productive or not. And it would flag a certain probability with each of those. So you would run that, then the expert would come after a first cycle, look at it again, and essentially focus on the areas where the algorithm has ranked them with a very low probability, and target those in priority and say, okay, I think that you were wrong on A, B, and C, relabel them right, and recycle them again. And through that kind of cycle, your algorithm gets better, and the experts gets immediately pointed at the areas that the code would have mislabeled with the highest probability. So they kind of enhance each other, and this is why we're talking about true interfacing here. And as you go as an organization, you gain also the experience of that expert, because as he uses the tool becomes smarter and smarter. So that's one of the examples. We have used this, and it has greatly enhanced the whole labeling process, and also the whole process of quantifying non-productive time for drilling. A lot of these examples are going to be borrowed from oil and gas, because this is the things I know what to talk about, but hopefully they apply to other industries as well. This is taken from one of our most recent projects. So rig, I don't know if you know what an oil rig is, but essentially it's a big piece of metal that is used to drill hole and complete wells. And we were, as Praveen demonstrated, asked to look at a lot of their data and essentially try to find when their rigs were going to fail, because this results in non-productive time, which is a lot of loss of time and money for them. So if you could be predictive on when those events could happen, you could essentially have a significant impact on the baseline of these companies. And one of the first things that you need to do is understand in what state you are. You have different phases in drilling. You're not just drilling the whole time. There are a lot of intermediary steps, whether you would be cementing or whether you'd be circulating some fluid. And essentially, it was very important to properly classify those different phases, because they all have different signature, and you could be trying to optimize on a certain signal while you were drilling, when actually you were not drilling at all and you were doing something else. So it's it's something that the companies were again convinced that they had a proper classification of all the different phases, and by looking at it, we were able to find out that it was completely wrong. So we started designing algorithms and rules to do that classification. And this is an example of how we did it in a heuristic manner, where we program essentially a set of rules saying if you are between this and that number for that type of metric, you will be into that phase, etc., etc. But we also experimented with a similar approach of training, where you would just put an expert in front of it and you would kind of label different phases, and the program would start learning what is pulling out versus tripping in versus circulating, etc., etc. So from there, essentially from a raw signal, you're able to reconstitute a story, and you start having a whole different discussion, because it's not just about the data anymore. You start having a discussion about what happened during that phase. I can see from your data that you were supposed to be drilling, but something happened, and then you start generating insight. And a lot of the data that didn't even seem relevant to you before that suddenly has a lot of importance, and you start really adding value. So I'll go into signal processing, which is one of the most classical approach to data preparation. There was one question, I believe, on denoising, and this is exactly what we're going to talk about right now. So on the same issue of drilling, we saw that making prediction on the raw problem could be too challenging at first. And what you see is the raw signal that is represented up here. And it was very noisy, and it was very hard for us to, at first, pull a predictive model that would allow to essentially forecast when those spikes would happen. So one of the approach that we took was to decompose the signal using wavelet transforms. And what you see are the different levels of transform, which essentially smooth out your signal and kind of emphasize some of those features. And once you went down to a certain level, you were now able to feed that through a deep neural network that we call an LSTM for long short-term memory, that are networks that are very well tailored to do prediction on time series or every kind of sequential model. And this denoised signal turned out to be very well matched to the data. And so that was kind of a starting point for us to do this whole exercise. And what you see here is essentially the trends of the actual data versus the prediction, which was extremely and a very good correlation here. And what you have are the separation of the data between the training in yellow, the validation set, what we call validation set in green, and then the test set in red.
Quick question.
Yes?
When you combine the features you mentioned and the waves together, and then you did the processing?
So no, the processing was done, so yes, the features were all, so all of the ones that were noisy were essentially transformed into that space, but it's the response that was denoised mostly.
So my question is, the input that's going into this, is that a combination of features you extracted, these states, and then also the waves, or is it something else?
So those were all time series coming from different sensors that they had on the rig.
I see.
And the whole idea was trying to predict what's happening downhole from from what signal you have at the surface. So all of those are signals that are coming from the surface,
I see.
and what you're trying to predict is the lateral acceleration downhole, which is how much your drill head is vibrating.
Thank you.
So that was like a starting point, and then you could essentially invert back to the physical space, or use the fact that you have a predictive model here and kind of retract back to the noisy space step by step. And now, because you have a good initial guess, you essentially have a model that goes from a better start, and you're able to go back there. And the results that we got, again, were not perfect, but they were good enough for the customer, in the sense that they could predict the period of high vibration and segregate the high versus the low. So that was like something that they really appreciated. And none of that, I'd say, would have been possible without a lot of pre-processing work on the data. So those are traditional ways of cleaning the data. Now we're stepping a bit more into the terra incognita of data cleaning, which is how do you use AI, how do you leverage AI algorithms to do the data cleaning. This is a personal project that has nothing to do with industry, but I really I'm a fan of boxing, and I wanted to essentially create an agent that would act like as an assistant coach to people who would be interested in perfecting their boxing style. So the point of reference was to look at professional boxers with very emblematic styles, and kind of try to mimic or match those styles with the ones of the average Joe. And so the task as a whole seems extremely daunting, right? Because you're talking about a very noisy space, many moving parts, and I was able to get to the level where I was able to recognize the style of, let's say, Muhammad Ali versus Mike Tyson, just based on footage of those two boxers. And I was pretty happy about that. Obviously, it's not like the end goal, but I'm going to take you through the different steps. So the first step is to recognize that there is a lot of footages available, a lot of, I would say, semi-public data for boxing match training. Just going through YouTube or a couple of movies, you'd be able to find all of that stuff. But this data is extremely noisy. When you look at a boxing match, you'll have people in the public, you'll have a referee. So how do you recognize first the boxer of interest? So we used a open pose algorithm that essentially extracts the skeleton of the existing humanoid on the photo or the footage. But that again was extremely noisy. You had people that would be sitting in the public against the referee. So how do you first recognize who is boxing versus who is not boxing? So we start by essentially creating a machine learning algorithm that would be able to classify boxing versus non-boxing posture just by looking at photos first and feeding it photos of people walking, doing gymnastics, swimming, playing basketball versus boxing. That would get to an accuracy that would be high enough that you'd be able to now say, I'm going to pass all of my footage through that algorithm. And now all of the skeletons that I'm going to extract have that boxing posture. The next step is like you always have two boxers on a footage, typically. So we went through unsupervised learning, as Praveen was talking about, and clusterized the different postures so that you would be able to say which boxer has his hands up, which one has hands down, leaning forward, leaning back. And start essentially subdividing your data set into smaller clusters where you can run a more precise classification problem. And then after that, once this was done, you were essentially able to take the algorithm and run it through hours of videos of Ali or Tyson boxing, and you'd be able to essentially classify whether it was one versus the other. The next step, obviously, would be to try to do that on other boxers and then compare with an average Joe to see whether you're like a 10% Ali and 80% Tyson or things like that. But that was just a pet project of mine. I thought that would be interesting to share. And this takes us to so the first problem that I was talking about the sparsity versus generalization. So we have a whole new generation of machine learning algorithms that are called encoders, and more specifically autoencoders. And the whole idea is, so dimensionality reduction is something that has existed in mathematics for probably centuries. You're talking about principal component analysis, SVEN, things like that. They typically are restricted. I mean, they are deterministic, and there are a lot of restriction in the type of reduction that you can achieve. In encoding, you essentially pass the data through a network that is converging, and you essentially take a bunch of features and reduce them into a bottleneck of a couple of tens or hundreds of features that will represent your data. And if your network is predictive enough, it means that your encoding makes sense and you are able to extract the features that are important to make your prediction. And those were at the center of, they had like quite a bit of success in natural language processing. I don't know if you've heard about the word2vec algorithm or the sequence2vec, where you essentially take words and associate them with a numbered vector. And now you can compare or combine them, and they were a big part in the acceleration of our machine translation system and others. So the idea here was to apply the same concept to reservoir engineering. Reservoir engineering is just the study of the subsurface in oil and gas and how oil flows in the porous media. So typically, you have a lot of data in those systems and different types of data. You have high dimension representation of the subsurface based on imaging techniques and geostatistics. And you also have data that has high temporal resolution but low dimension. So how do you merge all of these things and create a fingerprint of a reservoir? is essentially what we did in this project. And that resulted to a tool that is actually, I think, quite useful. Has been, again, a pet project of mine for the past year and a half, which allows engineers to rank different assets. And I feel that this message will resonate to executives. Typically, the analog ranking is a very important process in screening of different projects. So you will have like 10 fields to review, and the actual process right now is to log 10 gray-haired guy into a room and ask them which one is the best. And based on their experience, they would say, well, this looks a lot like what I worked on in 1985, and it displays the same kind of features, so I think that we should go with that. And this other geologist will say, no, I think that it... So it's essentially a discussion of experienced people. There is no quantitative workflow to do this. And I feel that by using those encoding techniques, we can now extract the important features coming out of those reservoirs and start having more discussion about numbers and less about opinions. And so we tested that tool and was able to take industry standard approach that essentially would predict the potential value of an asset based on people's experience and improve the accuracy of prediction by a threefold just by using those encoding techniques. So there are a lot of rooms where all of these technologies can be applied. Again, it's really finding like the niche problem that needs to be solved and where the status quo is just not satisfactory right now. So again, I hope that through this presentation I have conveyed the message that I'm not a skeptical of data science. I'm just coming from a world where trying to overly simplify things and getting onto like a hype about data is solving everything just didn't work. When you have large amounts of money at stakes, when you need to justify every number that you're presenting, you cannot just rely on a pile of data that you would steer through linear algebra, right? You would need to back this up with real heuristic, with intuition, with things that are amenable, that are explainable. But this being said, there are still a lot of sub-problems that present huge opportunities for companies that start working in that sector. Where just the current status quo is just not optimum, and where you can bring a lot of improvement. So I have taken you through a bunch of those different workflows. All of them follow a certain data quality framework. I don't think it's really important at this point. I'm going to jump to the summary, which is the mission of the data scientist is it to model and frame a problem? Is it to just visualize? Is it to create workflows and representation of your data? I hope that the different examples have shown you like the different aspects of the job. There is like a holy grail, which is we would like to automatically generate insight, but is it really the things that we're trying to do here? Probably not. I hope that I have made that point clear. Causality and reconnecting the dots is still a very important, especially when it comes to again, industrial application. So quantifying a number of clicks and sending the wrong ad to someone is not something that has a huge impact, right? But making the wrong decision on a multi-billion-dollar project has. So it's a whole different range of constraints that we are after, and they call for different approaches as well. So I hope that I have clearly conveyed the message, and if you have any questions, please don't hesitate.
Questions? Yep. Just a second.
Maybe I'll ask a question. This is very interesting, sometimes deep and hard to follow. So if we were to imagine we have a problem in front of us, let's make it a simple problem. I want to recommend restaurants. You and I starting a company, and we want to recommend restaurants to people. Now, there's a lot of data from people going to restaurants and reviews and things like that. The way you describe the world, there seems to be a lot of choices. I can go and analyze the data and extract features, and then based on that, build models, etc. I can also go the automatic way of learning everything. If you give me a sense of how do I make those choices before I start my startup to recommend restaurants, it'd be kind of interesting for me.
So that's more of like a consumer kind of problem. And again, it differs from the industrial applications that we're talking about. But my intuition on this is because the amount of data is so large, and because you have so much room to try, going the route of going big data and start like making suggestions based on a set of very simple features, but kind of let the data drive it, seems to be the approach that would eventually pan out, because it hits the right compromise between the effort that you're going to put in creating that model, and at the same time the depth and the accuracy of the prediction that you're going to make. But again, if your problem is just to recommend a restaurant, I feel that this is a problem that is very generic. But if you were to essentially go into more depth and provide different kind of prediction and recommendation to people, and I mean, I don't know, different restaurant for a certain mood, or how do you pair up this and that, or what kind of food would you order at that restaurant, then I think the whole feature engineering would become more important, right? So, no.
Any other questions? Going once or twice? Great, thanks, Cedric. So,
well, thank you very much for having me. Today and right now I'm going to go into a little bit of a deeper dive, peel the onion a little bit more, so that you can start to use these core concepts behind machine learning and deep learning to participate in conversations, engage in decision making, that it's important to engage in structural shifts, to lead these shifts in your current companies, in your future companies, to get machine learning into the forefront across your organization. You know, when I talk to data scientists and engineers and entrepreneurs, giving them advice about careers or organizational structure, what I like to tell them is it's really important to align yourselves with CEOs and key executives that are able to engage in those conversations. And so that's part of what I hope to impart today. A little bit about my own background. So I've been at this intersection area between neuroscience and signal processing and machine learning for quite a while, for about 2 decades. Academic career at Georgia Tech and University of Maryland and ETH Zurich. That was focused on neuroscience, auditory neuroscience, focused on neural networks, focused on artificial intelligence, and also neuromorphic chips. So these are very power efficient chips that compute functions relevant to AI systems in a brain-like manner. And over the last 14 years in Silicon Valley, that's pretty much been my career. I've managed to stick with it. More prominent example of that was algorithm architect of a company called Audience Incorporated. We started with a model of the human auditory system. And at the end of the day, we developed an intelligent audio processing chip that was sold into the iPhone and the Samsung Galaxy. We sold over 1 billion chips and IPO'd. Another much closer to the ground example would be my work over the last several years with conservation metrics. So this is a small Santa Cruz-based company that uses deep learning to help to automate endangered species conservation. So they They use remote sensing data, like microphones out in remote areas and cameras, to estimate population trends and to use that to improve conservation outcomes at the landscape scale. And I'm here today because of my work with 2predict. So we are helping companies to bring machine learning and deep learning into the forefront of their organizations. Okay, I've got a multi-fisted. So I'm going to talk a little bit more about what machine learning is. Deep learning being the Ferrari subtopic within machine learning. Try to set everybody's on the same page regarding currently impactful applications, and then start getting into the details of the basic concepts and machine learning model types that I strongly believe that you should be able to talk to people within your organizations about. Because these things do impact, at the end of the day, they do, because there's such a shift going on, the model types, the data, the how they use the data, how you have to collect data, how you have to audit the data, the computational frameworks that are required to process these data and to train these models. That impacts computational infrastructure in your companies. It impacts spending decisions, right? It impacts hiring, probably more than anything. So very important to engage. So what is machine learning? And some of you know this already, or you know kind of what machine learning is at a high level. Really what machine learning is you're learning a mapping. You're learning a mapping between some input space and some output space. What is a space? It's an input space is a domain. It's like, okay, what type of data are we looking at? How much of the data is going in? So how are we describing a house? We're mapping a house to a house price. How are we describing the house? Are we describing the house by a picture of the house? Or are we describing a house by square footage, height, number of windows? That is the input space. So deciding on what the input space is. And what the output space is, right, yeah, it can be the price of the house. It can be the category of house. What style is this house? It can be an estimate of the square footage, right? So there's all kinds of different types of input spaces. Some are more continuous values, like the size of it. Some are more categorical, okay? There's 5 styles to choose from. And the thing is about the advances in machine learning these days, these, especially with deep learning, if you have the data, you can learn very, very highly complex nonlinear mappings, like, okay, input space, somebody's sketch of a tree, right? And the output space is actually a pretty detailed 3D, computer graphics rendering of that tree. Where could this be used? Well, I mean, there's all kinds of different places this could be used in design, in gaming, right? So that's what's become so exciting about the advances, that if we have some clever way, or if you have the resources to set up examples between an input space and an output space, you have a very good chance now of being able to train that mapping. But it's very tricky, right? It's not an easy button by any stretch, and that's why you have to understand who to hire, what compute resources to use. Deep learning, I spent a lot of time talking about deep learning because that's been a big part of my career, and it stems out of my graduate work in neuroscience and just trying to understand how the brain works. That's how deep learning came out of those sorts of investigations. And what's unique about deep learning is that, so you at the end of the day, yeah, you're through maybe something you think of as a black box. You're mapping an input space, like a face, to an output space, which is the identity of that face, the person, whose face is it. What deep learning is doing, that's most intuitive in image processing applications, is that you're simultaneously learning a feature representation and a classifier. So typically, before deep learning became prominent, those things were kind of decoupled. Okay, you have domain experts that understand image processing, and they go in and say, okay, these are the features important to describe images, right? Based on experience, I know that, if I filter images with little edge filters, right, I can pull out where the edges in the image are, and we know that edges are important for classifying the type of image. At the classifier side, it's like, okay, how do we map? So now we've described an image by where the edges are. We got to map that to the classification decision. Deep learning, what that does is it allows us to get much more raw in the input space, to put in raw pixels. And it will learn at the lowest level what are the important features. What are these simple features that are closer to the input domain? And then they tend to learn this hierarchical feature representation. As we go through the layers of the network, they become more and more abstract. So we have edges at the very beginning, but then we start to see that those edges get composed in various combinations to patterns that start to look like eyes and noses. And those then get combined to higher level features that are more like faces. And now we can, at the highest level, we start to learn how to map those face components into decisions about whose face it is. Ultimately, how far apart the eyes are, and the arch of the eyebrows, and the fullness of the lips. Like, that's all things we can describe, but those things that we see that these networks are actually learning through lots of input and output examples. Another example that really was an aha moment for a lot of people in deep learning, in that we can have these higher order representations and flexibility in how we train and manipulate these representations, was something called StyleNet that came out a few years ago. So in this case, there was a network that was trained on images, like landscape images, and both photos and paintings, like famous paintings of landscapes. And what they did was they created a network that was tasked with identifying what was in the image. So is there a house or a lake? And on the other side, what is the style what is the artistic style of this image? Is this a Monet? So we have a system that now has a feature representation that's important for both. And then what they did is they devised a method to then freeze the network and sort of take off the style component. So freeze what they call the semantic component, so what the categories of things in the images, and then manipulate the style. So with the semantic component constant, they could change from from all these different famous painter styles. And there's other examples of that just are illustrative. I mean, this was another one that came out a few years ago that was an aha moment for folks. That you could try to evoke these networks to tell you why it's making decisions, what things it's liking to see in these images when it's making these really complex, human level ability decisions. So this was one where they were training a network on a lot of pictures of different sorts of buildings, pagodas, and then they tried to manipulate the input using some optimization algorithm. What input would maximize the output of the network, so it's sort of the strongest signal of this sort of a building. So then you can see, I see what features it's looking for. It's these are characteristic features that you see in these images, and it should be able to do it no matter where it is. So it's sort of spatially independent. There's these characteristic textures, characteristic colors, and characteristic higher level patterns, like the roof shapes. So those are the sort of things that are now being automatically learned by these systems. I think by now, we're all somewhat aware of all the impactful applications. I mean, you can hardly turn around these days and start a company or start some new company initiative without making reference to some other related impactful application. I mean, certainly autonomous driving is among the most prominent because of there's serious capital behind it. It's seen to be a very a difficult but very, very big opportunity, and it's very technically challenging because what are the different tasks that you have to solve in this scenario, right? So these cars. I mean, I'm generalizing now. There's a bunch of different solutions, but generally, the car is given some 3D map of the environment that's already been pre-mapped using 3D imaging technologies like LiDAR, and it has a task of, as it's going through the city, determining where it is on this 3D map. So it's sending out sensor signals, using cameras, using LiDAR, and it's trying to figure out where on this 3D track it is. It's sort of like a, it's like a perceptual train, right? It's on a track, but it has to figure out using perception where it is on the track, and stay, within typically like a centimeter of where it should be. So that's one task. So, mapping those input features to locations. Other tasks involve identifying where street signs are and identifying what the signs are and what they mean. And obstacle avoidance. So where are the pedestrians? Where are the bicycles? Based on images, based on sound. And it has to do all of this in the car, right? It can't really today offload the computation into the cloud. So it has to do this under 10 watt, with an under 10 watt, let's say, processor on board. So this means dedicated silicon. So this has just been such a great example for the industry to get behind, because it's just it's so varied in tasks you have to perform. And it's very challenging compute-wise. And so it's whatever happens in the self-driving car market, there's been so much great stuff that's come out of it. Related topic. So people talk so much about self-driving cars and the opportunity, but it's also very, very difficult because it's such a complex environment, so high cost of making mistakes. Individual buying decisions to navigate, whereas we're seeing huge impacts already in mining, for example. So where we have autonomous construction vehicles now taking the place of human drivers to greatly streamline operations and with just some remote control operator monitoring things, transform entire landscapes. Of course, everybody now is familiar with DeepMind and the work that they did to show that their reinforcement learning agents could learn to play Atari games with no prior knowledge of what pixels are and what spaceships are and what the joystick is. It just knows that there's a score, and a higher score is better. So that was the first splash, and then they went on to more complex games like the game of Go, and they've been able to show, this thing that we've been talking about for decades being, a bellwether that a computer can, through simulation and through playing itself, in a sense, through millions of games, it can learn how to reduce this very complex input space and make decisions that end up beating the best players in the world. And that's all fun and games, but the same sorts of algorithms coming out of the same organization can be used to streamline data center efficiency. So this is something Google started to show a couple of years ago, that give this algorithm a PUE metric, which is just sort of like a high-level efficiency metric. Give it control over the fan speeds in the disk drives and the blinders on the windows and how cool the room is, and let it learn over many tries over time how to optimize all of those things together to greatly decrease the power consumption in their, in Google's own data centers, which, they spend, I don't know what the figure is, but, obviously billions and billions of dollars. And now the UK has started to talk about using this same sort of approach across the electricity grid in the country. So this is closer to my own area of expertise, coming out of auditory neuroscience and developing auditory processing chips. A lot of my colleagues ended up in Amazon working on the Echo, and that is now, as we all know, a prominent part of many people's home lives. This is something that's close to my heart. This technology that I mentioned earlier, that you can put these microphone boxes out into valleys in Kauai, and those things can determine how these endangered species populations are doing as they do different conservation actions, like building artificial nests or putting up fences. And also they can not only determine what the sound of the birds are and to map, like, overall, okay, I hear all the birds and this is what it means in terms of the population health, but we can also monitor things like the birds hitting the power lines. So there's a critically endangered bird called the Hawaiian petrel that's been for years being killed by coming in and hitting these power lines, and it's very difficult to determine the scale of the problem in such rugged terrain until you put these automated systems out. And not only have they been able to tell that there's 100 times more birds being killed just by listening to it, in an automated way 24/7, but they've been able to use that data to develop better models for the habitat distribution. And they understand, okay, now that we're doing this new development across this valley, there's a much higher likelihood of there being that population there. And I happen to know from all this data I've collected that power lines should be undergrounded there, or they shouldn't be in at this height, or I should illuminate the lines with lasers. And so these are various mitigation operations that they're actually doing that are transforming development decisions in Kauai. Face recognition, is something we all are aware of. It's been very, very important for Facebook and Google Photos, but at the flip side of that, it's being increasingly integrated into surveillance systems, and so it's becoming increasingly difficult to be an anonymous citizen. Fake news, so one of the first applications of machine learning that was impactful was in spam filtering. So, email comes in, we extract features having to do with the spellings of words and which, special characters are in the words, and we can determine, okay, based on spellings, the way these sentences are structured, this is more likely to be spam. Now that sort of thing is starting to make its way into fake news flagging, which I think we all probably agree is important, but it's also very dangerous, because do we end up just filtering out half of the news that half of the people don't want to see, right? And this is in a way driven by the who's in power in these companies and at the federal level. So that's a big conversation that's going on right now in machine learning, is how to avoid baking in these biases. New molecule synthesis, right? So input-output mapping. So we know, okay, we have lots of examples of molecular structure and how it and the related reactivity of the molecule, and now we can start to use methods that propose based on lots of data and analyzing the statistical structure and how it's related to reactivity in a way that we cannot perceive. Then it will start to propose new molecules that have the right sorts of structure, and then then the biochemists can go and test those. And the idea is that, because right now it's sort of random search, or it's sort of human intelligence driven search. But the idea of these methods is that we greatly reduce the number of experiments that we have to do and the R&D expenditure to come up with new molecules. Yes?
How many use cases have been proven out with new molecule synthesis? Is this very pilot stage, or is it well developed?
Well, I can tell you that I feel that it's well developed because the startups that founded a few years ago when I first started to follow this, right? So they're still around and they're thriving. Some of them have been acquired. And more when you talk to these biotech companies, they talk about using these methods, and they've started to publish papers using these methods. Now, can I name specific molecules that have been developed using these methods? I cannot. I mean, partially because I haven't been closely tracking that aspect of it, but also that these companies tend to be very secretive. That's actually been a problem in that industry. So, a big catalyst in image processing had been ImageNet, that there was an academic group at Stanford and other groups, but mainly this academic group that finally just sat down and said, okay, we're creating a huge labeled data set, so we're just going to assemble a couple million images across all kinds of images on the internet, and we're going to label it, meaning that we're going to tell the computer exactly what that is. That is a steel drum, right? That is a dog. So that in around 2011, 2012, when the compute infrastructure got to the point that we could start to use deep learning on a huge data set like that, that was a huge catalyst. In biotech, it's from my understanding, there hasn't been as much open data, right? So that these companies are much more protective of their data. They really think of it as their intellectual property. So they're more secretive. They try to keep things internal. Yeah.
Thank you.
Yeah. Are you in a biotech company?
I deal with many biotech
Okay.
as customers, and I used to be in that industry. So.
Yeah. Yeah, so that's, just as an aside, that's been something that I've been wondering about for years is, I think, there's probably an acceleration that's possible there if there would be more data collaboration. But then, because that's really thought of as fundamental IP, how to compromise, right? So there's been techniques in machine learning to try to bridge that compromise where you essentially there's some privacy knob. Right, so you can have, there's a technique called differential privacy, for example. So you can kind of it's a way of keeping the data private, but sharing features that you learn from the data in a way that preserves the privacy of the data. It's often used with user data, right? So they try to do it so that, okay, if you dial up the privacy, then it's much more difficult to determine, for example, the identity of the person based on the features coming out of this filter. But also, you tend to do a poorer job learning, so it is kind of a sliding scale. And I wonder if something like that might be useful in that sector. Right, so the same sorts of techniques that are used to identify things like in Google Photos, to search photos, the very same sorts of techniques with different data can be used to identify tumors. And,
Sorry, second question.
Yeah.
Have radiologists done the equivalent of ImageNet?
Oh, yes. Yeah.
And is that publicly available?
There is actually much more radiology data that's become publicly available, yes, yeah. So I think, I don't have the names of those data sets in mind, but that is something when, if you Google it, you'll find these big CT scan data sets, et cetera. That, in that case, for whatever reason, a lot of that is coming out of these university hospitals and, so these research labs, so they've been much more open with their data. And they've shown, they've been showing repeatedly in the recent couple of years that they can outperform radiologists, right, in terms of the missing fewer things. It's still a complex task, and I think nobody's saying that we want to completely remove radiologists. I think we're saying that we can make radiologists better. We can make it so that as their cognitive load increases, they will miss fewer things. Okay, now I'm going to that next level where you're going to be talking to your engineers. You're going to ask them, is this a classification problem or a regression problem? And they're going to say, what? How did he know that? So anyway, supervised, so the machine learning tends to be categorized into three broad categories: supervised learning, unsupervised learning, reinforcement learning. By far the most successful of the three is up to date is supervised learning. If you have a problem that can be mapped to a supervised learning problem, that's very good news, especially if you can collect enough data. But it's not always the case that you can map it to a supervised learning problem. Well, what is supervised learning? It's what I was talking about earlier, that you have labeled data, that you know for a given input what the output should be. Now, the output can be a classification problem, so it's again two different classes. The intuition here is, in this simplistic classification example, so you're representing this data, whatever it is, by two different features. For each example, you can plot one feature versus the other. And then you can kind of see, okay, well, I have two different things here because the examples tend to be in different parts of the space. And so I should be able to draw some kind of a boundary between the two. And I know now that, so that boundary is my machine learning model. When I get a new example in, if it's on the green side, I'm going to call it green. Regression is different. The regression is the case where you have these continuous values outputs. So the label is the value, like the square footage of the house. But that also might be a very nonlinear function, right? It doesn't have to be some monotonically increasing or decreasing function. It can be very, it could be a circle, right? It can be a spiral on some multidimensional surface, but at the end of the day, it's some regression problem. So those are two fundamental kinds of labels, but you have some mechanism to get the data and to label them, right? Sometimes it's brute force, like I always heard about Google and their when they were first developing their speech recognition systems. Once it was shown how powerful deep learning was and how data hungry it was, they said, okay, screw it. I'm just going to hire people. I'm going to have 300 people in a room all day labeling things because I know that's going to lead to a good result. And even though it may be expensive to do that, I'll be making so many multiples on the system being successful. In other cases, it's sneakier. Like you might have some system that, okay, in your app you're able to collect data on user activity all the time, and you happen to know, okay, they get shown a screen, and where on the screen are they pressing? Well, that's a label. I mean, if you want to optimize, or if you want to predict. Given a screen, where is somebody going to press? And you have some mechanism to collect that data. Again, you're very likely to succeed nowadays if you can actually do that. Unsupervised learning is trickier. There's lots of advances here every day. Unsupervised learning is seen as more of a holy grail because you're not having to label the data. You're having to make less effort to label the data. It's inherently, you're kind of determining that there are different classes of things, like this case in this clustering example. Okay, we haven't told the machine that these are digits or what digits are, or that there's 10 different types of digits, but it's able to learn that, okay, there are really 10 types of things here, and I'm going to come up with some representation such that they will cluster in different locations. Now, you could use this as a starting point, right? If you have a decent unsupervised clustering algorithm, you put a bunch of data in, it starts to cluster them, and it presents it to some analysts who can say, okay, yeah, these are all the sevens. Like, I know these are sevens. I'm gonna draw a box around all those. I'm gonna label all those at the same time 7, right? So rather than individually going in saying for each example that's a 7, it kind of can speed up the process. And again, you might end up with a supervised learning problem, because that will be the most successful one. But this is kind of an accelerator. And there's lots of different examples that are coming out of the literature of learning the structure of language in a fascinating way, where we can start to do algebraic operations on sentences, and in generative modeling, where we learn a high dimensional statistical representation that can then be passed through an inverted network and generate new faces. So again, we haven't really told the machine what a face is. We've just shown it many different examples, and then it starts to see, okay, I understand the structure of a face. In fact, I understand it so well, I can generate new faces I've never seen before. And then we have reinforcement learning, which, if unsupervised learning is a holy grail, reinforcement learning is really, it's godlike in its potential, because we have a system that is able to both observe and act on the world. And in fact, the way it learns is by acting, observing the result, and it learns both from acting and observing the result. It is learning the representation of the world, starting from a baby's eyes, not knowing what anything is, and it's also learning how its actions affect the world. What is governing the system? What is governing it is it's some high-level goal, right? It's some policy function. In the case of Atari games, it's the score, but in general applications, it's something that tends to be much more meaningful and much more complex. In environmental conservation, it may be the biodiversity of a region. We saw another example with data center efficiency. So the reason why you use reinforcement learning systems is that you're in a complex environment. I mean, the same thing with self-driving cars. You're in a complex environment. Maybe you need 1 trillion examples to learn. Are you going to label 1 trillion examples? How are you going to gather those examples? How do you know what examples to gather when the space is that big and there's so many corner cases based on weather, based on the road type, et cetera, et cetera? All little differences matter. So that's kind of where reinforcement learning comes in, is you now have a mechanism to explore the world and to both learn to perceive and act on the world in a way that is optimizing some high-level goal. Pretty much with all of these systems, you start with feature extraction. Cedric was talking about that a little bit, and so I'll just very briefly remind you in the conversations that you'll have, what does a feature mean? What is feature extraction? Well, so the feature is just the way you're representing your input space, and it's really broad. It's really broad from there, right? So a feature might be, okay, I already have a face. I have a face detection algorithm that's very good that can tell me the landmark locations of the corners of the eyes and the mouth and the chin. And I'm not going to use the face itself. I'm just going to use those numbers as my features. And I'll tell you in a minute why that's important to do that. But so yeah, so this was a some spectrometer image of a molecule, right? Yeah, so you get some spectrum out. Well, you can put the entire spectrum in, but you might happen to know, well, what's really important about this are where the peaks are. And the peak locations and heights are your features. I've talked about houses and how different ways. So that's what feature means. Dimensionality reduction. So you often do feature extraction to reduce the dimensionality of the data. Dimensionality of data is just the number of numbers that you're using to represent each example. So if you have a 100 by 100 pixel image of a face, and you're just putting in that image, those raw pixels, the dimensionality of that image is 100 times 100. So there's 100 times 100, 10,000 pixels. That's the dimensionality. The dimensionality of that input data is 10,000. But do you really need to put in 10,000 numbers per input example? And it's usually not a good idea to do that because there's this fundamental trade-off between the dimensionality of the input data and the number of examples that you're using to train a system and the complexity of the task, of this mapping task. Generally speaking, if you only have, let's say, 10,000 training examples, you're not going to want to represent each image by 10,000 values. You're going to need to, it's too complex. The input space is too vast. You're asking this computer, based on too few examples, to look at this vast space and figure out where to draw lines between categories. So ideally, you want to crunch it down to just a few numbers that are important. The trade-off there is that, again, like you have some domain expert that says, oh, well, I think eye corners are important. I think chins are important. Maybe they are, but it's probably not the entire story. It's not what we're just, what our brains are alone using to make these decisions. So that's kind of the trade-off. Well, the other trade-off is just compute. If you're putting in 10,000 dimensional images and it's going through the the computing functions for learning and for predicting in production, there's just many more compute operations, many more multiplications and adds, much more power consumption required. So those are reasons why you want to reduce the dimensionality. A very simple way of reducing dimensionality for images is to downsample. So just put in low-res versions of those images. That is very commonly done. The trade-off is that you're obviously losing detail. A way of getting around that is using things like principal component analysis. So there you're not just putting some blur function and taking fewer pixels out of the image. You're actually trying to figure out, okay, these are all faces, and so I should be able to learn what these they call them eigenfaces. Like I should be able to learn across the entire image. Okay, what is the number one most important image? If I average across all these faces, what's the number one most important average face that can be used to describe the variance in this data? So that becomes the first one, and then you subtract that out, and then you kind of go from there. And lo and behold, you might only need a few dozen of these eigenfaces that together, you would add them up in various combinations to come up with any face. And so then you just have to represent to the input of your machine what is the score of each of these eigenfaces. So that becomes your input dimensionality, just the number of eigenfaces.
I got a question here.
Sure.
So, yeah, it's basically if I have X number of features, how many samples am I going to need? Is it like 10 to 1 or is
10 to 1 is often a rule of thumb. Yeah. It does depend somewhat on. That's like rules of thumb are important, but yeah, it's not to say if you're outside of that you will not succeed, right? Yeah, empiricism is so important in the field right now people just try it. If you can, you'll try it. But in terms of making quick decisions, right, yeah, the rules of thumb are pretty important. So then what are your engineers doing as they're training these systems? This is a real trick, actually. This is not easy to do, because if you have a very difficult task, so you have some training data set that's large enough, given the number of input features that you need, your feature dimensionality. And then what you do is you have some method of training training your network or training your model. These tend to be iterative approaches, so you're looking at a bunch of data, making a step in some direction, and then you validate. Okay, this is now the current state of my model. I have some validation data, some test set that I'm using to figure out how I'm really doing. You can ask how you're doing on the training set, but that's not really fair, because many of these systems, they overtrain. So they just learn the training examples by heart, but you show it something it's never seen, then it totally craps out. So there's methods to try to mitigate that. You train, you test on your validation set. You say, okay, with this held out data set that the model's never seen, I'm doing pretty well. Then you go out to the world and you deploy it, right? So okay, you're you're out in the world. So this is the real test. You're out in the world, and now you see some errors being made. How do you correct those errors? Well, usually the errors go to some internal data scientist, some analyst that says, okay, I'm going to try to get some intuition about why it's failing, but at the end of the day, I'm going to take data, failure cases. I'm going to say, okay, well, there's 3 different failure cases. I'm going to wait till I have 1,000 examples of each, and I'm going to put it back into, I'm going to put some in my training set, some of my validation set. At that point, it's not really fair to test it on the same test data, right? So you have to go back out into the world and do some real tests again. So this is what is, I think a fundamental trade-off in the use of machine learning systems, and, in these production systems and algorithm development now. You have to have this infrastructure in place so you can train, validate, go out in the world, test, have mechanisms to get the data back to you, to analyze, to retrain, et cetera. So retrain is now what we see in these large ML-first companies. And a big part of how they measure how fast they can move is how quickly can I retrain. And that really is largely to do with the compute infrastructure and the use of GPUs and the use of distributed computing, et cetera. So the last part, I'm going even deeper. I will try to keep this at a high level, just so some of you know this are very well already, I'm sure. But I guess what I want to say about this in the beginning is that there's a lot of talk about deep learning. Deep learning is like the sports car. You don't need a Ferrari to go down and buy toothpaste at the general store. If it's there's value to the empiricism that these methodologies impart on your organization outside of using deep learning, right? You can use simple models, like if it's a relatively simple task and you have good features, you can use simple models. And the good news is that these will retrain, in a second, not 2 weeks. So K nearest neighbors is actually a great little machine learning algorithm. And it's also very intuitive. So you have your feature space. In this case, again, it's two numbers, right? Could be house area and zip code. And you're collecting training examples. You have labeled examples, so you have 3 categories of houses. And now, what do we do when we're in production? Well, we have some new example that comes in. How do we classify that thing? Well, we have some distance function. Could be Euclidean distance, just like the sum of the square, the difference between this value and the values in each of these clusters. And we just average. We just allow, we allow each example in the neighborhood to vote how many it's closest to. So, this is closest to more of the orange circles, so we're going to say that's an orange circle. That's a classification problem. In a regression problem, we might average the attributes of these to say, okay, this is the attribute of this one. Like this is the value of the house. That's all k nearest neighbors is. Decision trees. Also highly recommended in cases where you really want interpretability in your system. So you can structure these such that, so all of these, so this is decision tree, what was it? It was like, should I go out, should I go out or not? Should I stay in or something like that? So, or should I go in the restaurant? Anyway, point being that there's all these features. So yeah, features of describing the task. Something describing the patrons inside, the wait time estimate, are you hungry or not, or is there an alternative, etc. So these are all features, and then we have labeled examples, so we know the result. Yes, you're going in. No, you're not. And it kind of it figures out the most impactful, starting from the most impactful feature and where to draw the line. So based on your input features, yes, you're either in none, some, or full, and then you go to the next step, and there's multiple branches depending on which you decide. The nice thing about this, so if you're trying to make a decision like to give somebody a loan, it's not a black box. Or if you're trying to make a decision if somebody has cancer in their radiology scan, if you have the ability to use a decision tree and it has pretty good results, it's often very good because you can kind of go back and say, yes, that makes sense. Oh, isn't that interesting that is the most impactful feature, right? And isn't it interesting that if I've made these 3 decisions, that this next one is the most impactful? And you can kind of start to streamline operations based on interpreting how the system is coming up with decisions. But the downside is that, the decision trees tend to be less effective on very complex tasks. Support vector machines is something that was the king of machine learning until deep learning came in. What I can say about support vector machines is that essentially, you have some input space, so some 2-dimensional input space, 2 numbers. Support vector machines figure out how to draw a line to separate the 2 classes. But it does it in a way that maximizes the margin between these 2 classes. So if we want to linearly separate these 2 classes, we could draw this blue line, right? So it's perfect on this data, but how well is it going to generalize if there's noise in the data? We would really want a decision line that somehow is maximally separating the 2. So that's what SVMs, support vector machines, do, and they do it in a tractable computational manner where there's a single unique solution. What about this? So can we draw a single line to separate these, a straight line to separate these classes? Well, no, it's a much more complex function, but what really led to the advances in SVMs is something called a kernel trick, where we learn to map the data onto a higher dimensional space, and figure out, okay, even if on this picture, on this 2D picture, we can't draw a single line or plane to separate the two, we can find some higher dimensional projection where we can actually separate the two out. And so there's different kernel functions that are used, right? So there's a kernel function that was invented just for separating out this sort of kind of data where, you know, there's rings in the feature space. And so there's many kinds of kernel functions depending on different structure of data that people have determined are characteristic. You know, and there's a trick to compute, you know, there's a trick to actually compute the optimal separating hyperplane that you can solve the problem without actually having to project the data to this higher dimensional space. I know that's getting a little bit into the details, but you know, when you hear people talk about the kernel trick and SVMs, that's what they're talking about. And you can see why it would be so powerful in being able to separate really complex data. But that's, you know, then deep learning came along, and it kind of it ended up supplanting SVMs because deep learning methods just continue to learn. The more data you put in, the better it does. And sort of like has a nice linear property. You know, the more data you put in, you're learning for linearly more time, and you're doing linearly better in some sense. Whereas SVMs and every method before deep learning was much poorer. You know, it would reach some ceiling where it just can't work with that high dimensional data anymore, or you know, it's just not computationally scalable. So you know, the number of multiply adds you need to solve the equation just blows up to infinity. So deep neural networks, among the many other advantages, really probably the prominent advantage is that it has these nice linear scaling properties with the amount of training data. And it has the capacity to learn in these very high dimensional spaces, like the brain. What's so great about deep neural networks besides that? Well, we have something that is very commonly used called transfer learning. So remember I talked about deep learning. It co-learns a feature representation that gets higher and higher levels of abstraction as you go deeper into the network, and then it learns to map the abstract features to decisions. Well, we could just remove, if it's a sufficiently complex task like identifying objects and images, it turns out that those abstract representations on a certain task, so we have some like ImageNet, you know, the steel drums and cats and dogs, and so what we think is that we're learning a pretty general good representation for images. Yes, for that particular training task, we've mapped that onto the set of classes that we have for that task, but we could actually just remove that part, the classifier part. We can put those features that are very good and put it into some new task. So let's say we have some new task where we only have 100 examples. Well, we don't have to relearn the features. We just have to relearn the classifier. And to do that, you need many fewer examples because you already have these high-level abstract classes. In fact, you might be able to put an SVM on top. And an SVM, again, is going to be faster to train. You know, will consume potentially less memory in some small footprint embedded device. So that's what they mean by transfer learning. You know, you have some system that you're taking off, maybe off the shelf, you know, that's being hosted somewhere on the internet. You're using that as your starting point, and you need very few examples to do a relatively good job from that starting point. You know, it's also kind of a network effect within your company. If you have all these different tasks, you can start pooling, and you know, you can start using transfer learning within your organization to accelerate. You know, you already have good starting points for new tasks. Multitask learning is kind of similar. It's just that you may have, let's say, you have 10 different tasks that you have labeled data on, but you don't have that much data for any given task. Well, it turns out you can do better on any of the individual tasks if you use a deep learning system to perform all the tasks simultaneously. And again, the intuition behind that is it's kind of pooling all the data. It's a good way of pooling all the data across all these different tasks, so you're learning a good representation that's kind of a general good representation across this kind of data. Deep neural networks is it's data agnostic, much more data agnostic than previous ML models. You can use the same compute infrastructure, the same learning algorithms for many different types of data. It's molecular data, it's image data, it's audio data. So you don't have to reinvest in compute infrastructure.
Where would you see the boundary between a deep neural network being a good use case for it and something simpler?
Mm-hmm.
Where would be like a gray zone of decision making?
Yeah, it's a little bit. Yeah, I'm trying to think of a rule of thumb, or it tends to be an intuition. It tends to be something like. You have to kind of evaluate how complex the task is. If you have a data scientist that can sit down with your data and let's say it's I don't know, it's an 8-dimensional feature representation, and they do some very simple clustering algorithm, and clusters kind of just pop out, or you do a scatter plot, and you see them, you pretty much see them a separation of classes, and right there and then you can pretty much say, okay, I don't really need a deep learning algorithm there. You can already see it in the data, and so I'm just going to kind of automate the optimization of where to put the decision boundaries using an SVM or a k-nearest neighbor system or something like that. It's also the case that it may be a complex task, but you just don't have enough training examples, right? So there's a deep learning, the positive of it that I was saying, it just keeps trucking along. The more data you have, the better it does. But if you don't actually have that much data, it's not going to be better. Yeah. So there's ways of making it equivalent. So in some cases it's just way over. Some cases you throw a deep neural network at a small data set, it's just going to overtrain to that. It's essentially going to memorize all the training examples. It's going to do a very poor job at generalizing. But there's methods called regularization that I haven't even gone into yet. But there's methods of making it so a deep neural network will not overtrain and will generalize better. But still, there's just not enough examples for it to learn that highly detailed decision function. So it's going to learn some really blurry decision function that pretty much any simpler ML model could learn. So why not use, the question is, why not use a simpler function on it? And so yeah, if you're highly compute constrained, if it's a big win for you to, based on training time or based on where this is being deployed, the memory and compute restrictions of where it's being deployed, then so go for if you see that situation, go for the simpler model. For me, it's like for me, it's kind of like a hammer where everything's a nail. But it's like, it's just, for me, it's a pain I have my deep learning toolbox, so it's kind of hard for people to switch me off of it because I know I can reuse the same tools over and over. I don't have to context switch, So I tend to fight back against people who say, well, that's too few examples. Don't use a deep neural network. It's not going to do well. It can be equivalent if you put the right guard measures in, and so you don't have to. You could use the same compute infrastructure, the same tools. Yeah, the caveat being, again, you may be wasting time training, and you may be using too much computer memory in deployment.
Patterns not obviously self-assembling or self-emerging.
Yes.
You might say, okay, go from the simpler to the more complex computational strategy.
Yeah.
But if you go to that more complex computational strategy, you may be processing noise unless you're really careful.
That's right. That's right. And you know, in practice these days, I mean, I've said empiricism a few times, but yeah, that's because all of these methods are all open source now, and you know, the big tech companies have been very proactive about, you know, for various reasons, about making these tools available. It is relatively simple to just try it. So that's what a lot of people do.
And why do you think these tech companies are making these tools open source? Why is TensorFlow open source? Why is Google Brain publishing everything? When the biotech and pharma companies are trying to hoard the information, is it just a cultural difference? Is there an underlying strategy?
Well, one big part of the strategy explicitly is recruiting, but you know that that would be the case. I mean, that should be the case, I think, in biotech. Yeah. So but that is one of the strategies, you know, in getting more tools out in the world. Once you establish that you can use these methods on all different kinds of impactful applications, and you need the people to do it, you know, still today you need the people, the researchers to do it. It's just a nice way to set up an ecosystem where, you know, researchers are showing what they can do with your tools, and you know, you can onboard them very quickly. Because while things have gotten simpler over time, but you know, there's still hiring is such a you know, such a tough thing. It's tough to find people. It's tough to retain people. The onboarding process, you know, can be months before somebody's productive. So that's a big part of it.
I think it's also there's
Yeah.
tools and there's models. So models are even by Google kept secret, but the tools like TensorFlow are made available because data is key, and Google has the data, so they're not sharing the data. And similarly, pharmaceutical companies are not sharing the data or the model. They keep all that secret.
Yeah.
How would you define the model? As like a data processing strategy, or?
Well, yeah, models. I mean, the models are, for example, in Google Photo. You know, the models that can recognize faces and objects and images. They have models for that. Yeah. When Facebook gets a new image in, they run that image through 4 or 5 different models, and that may have changed. A couple years ago, sorry.
Cedric gave an example, right? Using the LSTM and the AD, all of that pre-processing. I mean, isn't that all a model?
I mean, a model is something that is doing this mapping function. It's mapping some input to an output. And now there's just so many models for so many different tasks. So like I said, yeah, Facebook is running the image through 4 different models. One is looking for faces. One is looking for, I don't know, it's trying to estimate where the person is. Those models, in a lot of tasks, well, yeah, it's like, why do you do this? I mean, in some models, you know, some models have to get to a certain level of accuracy where they're actually useful in some product. Like speech recognition, you can't, if you have 20% word accuracy or word error rate, people won't accept it. You have to get it above 95%, you know, and up, that kind of thing. And it is actually, it's tricky to do that because you need all this data. I mean, I'm sort of glossing over how much compute infrastructure, how much data, how much time to get a model that works really well, and then to go through this iteration process and retrain every 2 weeks. That's a lot of engineering time, a lot of electricity, right? So that, yeah. And given that it's so hard to get there, it's really valuable. Like, you know, well, you hope it is. You hope it's something that is actually driving a decision to use your product.
So are universities producing open source models?
Yes, yes. So there are open source models, and often they're used for transfer learning. You know, to start at some good place. It is pretty common now for a deep learning toolbox. You know, so there's all these deep learning open source toolboxes, and it's very common to have something called a model zoo. That first came out of this deep learning toolbox called Caffe. And yeah, it was just sort of, it was a nice little model marketplace, if you will. They call it a zoo. Yeah, it's not really a marketplace in Caffe because you're not buying models, you're just taking stuff off the shelf. There's many companies that have talked about creating a model marketplace, right? So to actually directly monetize models. So if I have, you know, as some individual or, yeah, so a small company have developed some really, what I think is a valuable model, I can put it on a model marketplace. And people can use it maybe per transaction, right, through API calls, or maybe they can rent out the model or have some exclusive use of the model. So that's, there's been talk of that for a long time. I've not seen that take off. But the model zoos have been very helpful for the community.
Thank you.
Yeah. I think I should stop there. I mean, if there's any more questions, well, let me just fast forward through what I was going to say. But I feel like I'm at a right level of depth. You know, you can within deep learning, there are different types of model architectures that are good for different types of tasks. Internally, they use the same learning algorithms, and they're kind of internally doing the same compute operations, but the overall structure, the overall graph is different across these different types of tasks. So convolutional neural networks are really good for images and other kinds of tasks where you have local structure, where you know the natural data domain. You have a lot of structure in local regions like edges. You know, not all data is like that. Some data is just a random collection of sensor measurements, and there's no local structure. So CNNs, as they say, convolutional neural networks, wouldn't be effective on those, but they are effective on images and other tasks like that, like even audio. Recurrent neural networks is more having to do with you have a sequence. So you might have a financial time series, or you might have a sequence of words. And sometimes convolutional neural networks do well on those, where recurrent neural networks, with LSTMs being a subclass of that, a very successful subclass of recurrent neural networks. Why they're recurrent is because to make a decision, you want to know the current features, so you're making an observation of the world. With the CNN, you would make an observation, a single observation, and you'd output a single result. Recurrent neural network is, okay, you have an observation, but you're also have this recurrent connection where your previous output gets fed back in. So it means that there's context that's important here, right? So based on what just happened, I'm going to change the way I'm mapping the current input to the current output. And these get really complex, so you have all these different ways of holding different things in memory for potentially a long period of time. Like with sentences, you know, the way you interpret the sentence might be completely different based on the first word. And you might not really know until you get to the last word. That's like one of the stereotypical examples. So you hold that first word in memory until you make this series of observations get to the last word. Again, that's the intuition, but what's so cool about these things, you don't tell it anything. I mean, you're just saying, I'm just putting in this, like I just have this potentially long sequence. I can tell you what the result should be, and I'm just going to feed in, a million of these, and it's going to learn what things to hold in memory, for how long, how to combine those across time. That's what these things are.
So question,
Yeah.
sorry. Thank you for letting me interrupt you.
Yeah, no, of course.
What the boundary between convolutional and recurrent neural nets? I'm wondering again,
Yeah.
kind of question. Imagine you have a video, which is time series,
Yeah.
but it's of images
Yeah.
and sound. So how would you process a video with a neural net? Which side of that would be on? Would you have a convolutional network of recurrent networks, or the other way around?
Funny you should ask that. That's exactly what I'm showing here, right? So that's the other cool thing about deep neural networks, because you're using these characteristic learning functions, and it's all about the graph and how you structure the graph. You can totally do what you just said. You can create convolutional layers that are feeding into recurrent layers, and therefore you can do a mapping function like mapping an image to a sequence of words, right? And so we just had a customer engagement where I used something like this because I believed there was local structure in the sensor data that I wanted to extract features from. I wanted the system to learn convolutional filters that were optimal for the task, but I also thought probably the pattern of those over long periods of time was important for estimating essentially time to failure for a particular type of machine. So a convolutional neural network by itself, if I'm training on 60 minutes of data and estimating some failure time, convolutional network wouldn't do well on that.
So how do you know if you over-engineered? Like, did you try it 3 ways? The hybrid way, just one or just the other, and see how the failure rate worked, or?
Yes, that's exactly what I did. I started with an LSTM by itself, and then I went to a structure where I had a convolutional input, a number of convolutional layers. You typically do more than one layer because, again, you're wanting to learn some kind of powerful abstract feature representation that you're then feeding into the LSTM that's learning what features are important in what order and how long it has to keep things in memory and things like that. So I tried both. I did try both, and I tried an even more complex variant. And the more complex variant had actually 2 input branches with 2 different types of features. Yeah, so I think I'm saying that because that's kind of like as a deep learning researcher, you're doing a lot of things like that all the time, right? And you sort of learn what types of structure is good, what types of graph is good for different types of data, different types of tasks. And it does end up being a lot of exploration. Yeah, unfortunately, yeah. I mean, that's like the good and the bad of it for me, because yeah, the good is that you now have methods at your disposal. If you have the data, you have a certain amount of experience. It's kind of fun to explore and find some new architectural variant that's doing the best job at your task, as long as you structure your tests appropriately. The bad of it is that, this, like, even the most experienced deep learning researchers, they never quite get to a level of truly understanding why something will work and when it will work. So you're always coming up with these new things that work, or there's things that are going against your intuition. And there's just lots of empiricism involved, which is why it's important to have a way to quickly iterate. That's why there is so much compute investment. And actually, to the previous point on models that I wanted to mention, your question was why does Google open source all the tools, right? So there's a recruiting aspect, and and other aspects that were mentioned. But another aspect is like now that because the compute resource is, having a vast compute resource is an enabler on these tasks. And you're doing a lot of exploration, so you're computing, these things. You're just, every time you do a new experiment, it's more computation. The average person doesn't have that compute resource in their house. What do? They use AWS, they use Google Cloud, they use Microsoft Azure, and these companies are obviously deriving a great amount of revenue from renting compute to you. So that's another reason to open source the tools, because they want to get you hooked on their tool set. But it's like the field has changed because the deep learning researchers, machine learning researchers, and data scientists, they're still scarce. They're still somewhat specialized, but it's much more now. How do I say it? Yeah, it's much more. They learn from examples. They learn from experience. Yes, I mean, there is a part of it where you understand the deep computational, the set of equations that you're implementing to do this learning. But at a high level, the person that's in the controls, the data scientist, it's now, I think the field is in a state where you can have these data science academies that are training more of an average person that's not going through a PhD to get this knowledge, right? They're not having to spend 4 years focusing on what is the statistical structure of images. It's more like, okay, I'm going to focus on how to drive this machinery that is now much more extensible across all these different domains. So it's a pretty interesting time. So I think I will leave you with that.